we've been discussing what goes on the outside of the sun. So, what goes on the inside as it ages? So, we know the outside swells up to be a red giant, but what about the core? So, you've got the outer parts of the sun that are red giant. We've got this core. The core is surrounded by a shell that is fusing uh, hydrogen into helium. And so the fusion's going on in the shell, not in the core. So the outer parts get pushed way out, and we end up with a red giant. But the question is, what about that core? The core is basically dead. It is mostly made of helium, and the helium is not really doing anything. It's just there. And so as you get more and more fusion going on in the shell, the helium, which is heavier than hydrogen, which is the byproduct of the fusion, is falling into the core, and the core gradually gets more and more massive. And so as it gets more massive without nuclear fusion in there acting to provide energy and heat to make it expand, it just gets smaller and smaller. Well, it can only get so small. Turns out there's a limit to how much you can compress something. And what limits it is something that we call the Pauli exclusion principle. Physicist that Enrico Pauli that explained this. So the Pauli exclusion principle says that no two types of particles that we call fermions can ever interact with each other and be in exactly the same energy state. The energy state is given by certain numbers that we call quantum numbers. So no two of them can be the same. And so what happens is that as the core gets smaller and smaller and smaller, eventually the neighboring nuclei, the neighboring atoms start interacting with each other. And when they start interacting with each other, then they can no longer get pressed any closer unless you have enough energy. And so now what does that mean? The Pauli exclusion principle applies, for example, originally to electrons in an atom. No two of them can be the exact same energy state. And so what happens is that the lowest energy, the electrons can only be one way or the other way, and so you only get two of them. So in order to get any more electrons in an atom, they have to be to a higher energy state. Well, that means they can be one way or another way, or they have enough energy to be acting as if they have angular momentum, and so now you can have six more of them in there, but then you can't do it again, so unless you get more energy. So you get more energy, then be one way or another way, or you get six more of them in there in various orbital configurations, and then you fill up that shell, and you have to repeat it again. And so you keep repeating. And so what happens is, as you start filling up these shells, you get more and more energy that allows you to fill up even more. And so the process keeps repeating and repeats with a periodicity. So if you were to make a table of atoms or table of elements that was in order of number of electrons, that table of elements would repeat periodically. And of course, you'd call such a thing a periodic table of the elements. And so that's why it's actually called that. But the same thing is going to happen in the core of the. So you have this degenerate core, and we call it a degenerate electron gas. So the core is almost entirely made of helium, and the helium atoms can only shrink until they're so close together, and then neighboring atoms interact. And so when they start interacting, you cannot shrink anymore. So this is a degenerate gas. It doesn't matter. You put more pressure on it, it doesn't shrink. In fact, a weird thing happens is if you heat it up, a normal gas will expand if you heat it up, but the degenerate gas, because they're hotter, you have more energy, which means that the electrons can be have more energy than one another, and so they can actually get closer together because they're not all the same energy. So a degenerate electron gas, if you heat it, it actually gets smaller. The other thing is, if you add more mass to it, it gets smaller, because what happens is that gives you more gravitational energy. And so a degenerate electron system does not behave at all like a normal ideal gas that you can learn about in chemistry. This behaves entirely differently. And so the core of the sun becomes this degenerate electron gas. So there's the core. Surrounding it is a shell that's fusing hydrogen into helium. Now that's releasing heat and energy. That heat is heating up the core. It lets it get a little bit smaller. The helium, because it's heavier, sinks in the core, giving it more mass, more energy, more gravitational energy, makes it get smaller. And so the core is gradually shrinking, and not very fast. It's just very, very gradually shrinking and getting hotter. Okay, so that's behaving differently. Eventually, if the core shrinks enough and gets hot enough, then the heliums will start fusing. So what happens is, we call this the triple alpha process. And so what will happen is the heliums, two heliums come together to make a beryllium. The beryllium grabs another helium and then makes a carbon. And so you end up fusing helium into carbon. So basically this looks like three heliums fusing into a carbon, carbon 12. So helium 4 is fusing into a carbon 12. And so that is the process. Now, it's important to note that for stars that are less than 0.4 solar masses, so these would be like the little red dwarfs, they do not ever get hot enough to start the process. So that means they end up, after they fused themselves completely, all the hydrogen fused into helium, and then they're done. They shrink down as small as they can shrink, and they just become a degenerate helium ball. Stars bigger than 0.4 solar masses, obviously the sun's 1 solar mass, is going to go to this next step in which it starts fusing the helium into carbon. So we call it the helium burning stage. Now the problem is the sun, because it's a degenerate system, once it starts fusing, it doesn't do it gently. It starts fusing. That releases energy, which allows the core to get smaller, which makes it get even hotter and smaller, and starts the fusion to go even faster, which makes it get even smaller, and fusion goes even faster. And so you have this runaway process. And so the entire core suddenly starts fusing all over. Instead of gently, it overfuses, and we call that the helium flash. Stars bigger than 2.5 solar masses don't do a helium flash, because they just gradually get hot enough. They start fusing the helium into carbon without ever going through the helium flash stage. The core doesn't actually become degenerate. So the sun goes into this helium flash. The helium flash starts all this fusion process that allows the core to actually become a normal gas for a moment. And so it expands, the fusion stops, it shrinks, does another helium flash, and goes through several steps of the helium flash. The outside of the sun would momentarily get very bright over a period of thousands of years, then dim down again. So the helium flash occurs as helium starts fusing, and then what happens is that once it settles down after a couple of helium flashes, then the sun will settle down and start fusing into you'll have a core that's fusing helium into carbon, and surrounding that is a shell fusing hydrogen into helium. Surrounding that's the rest of the star. It's starting to fuse in the core again like it's supposed to, so it starts shrinking and heading back towards the main sequence. But it's hotter, so instead of going back to the same spot in the main sequence, instead it goes towards a hotter spot of the main sequence. And so if you were to plot an HR diagram of a whole bunch of star clusters that are in the process of doing this, you'd have some stars there, and so that we call the horizontal branch. So the sun, interior of the sun, right now, the interior of the sun is fusing hydrogen into helium, and the outer parts stay hydrogen. When it starts becoming a red giant, when it starts running out of hydrogen, it becomes a subgiant, and so there's no fusion going on. The core shrinks, and the sun kind of expands and gets bigger, and then what happens is you start fusing in a shell, so the outer part of the sun gets vastly bigger, becomes a red giant, and so the core has no fusion going on at all. It's just helium. And you have this shell that's fusing hydrogen to helium, and then what happens is that the shell ignites, and you start fusing helium into carbon. And so the red giant starts shrinking, and when you shrink, it gets hotter, and becomes that horizontal branch star. The lifetime of a star depends on its initial mass. And so there's a formula. The lifetime, the T here stands for time, the age that a star will live, is roughly 1.2 times 10 to the 10 divided by the mass to the 2.5 power. And so that's mass in terms of solar masses. This gives you the age of the star in years. And so that's what determines the mass of a star. So this is an HR diagram of a very old star cluster. And so originally all the stars were along the main sequence. The ones that were up here have left the main sequence. And so here are stars that were here are now expanding and be a red giant. Stars that were red giants that had a helium flash are heading back this way. That's what we call the horizontal branch. And so that's why the HR diagram looks like that. Interesting thing, turnoff point are the last stars on the HR on the main sequence here that have not yet turned off. Now, stars that are up here have already left and they've done their whole lifetime, and so they are off the main sequence. So those stars are off the main sequence, and that means that they are already dead. Stars that live longer than that, remember the higher mass stars die first, the lower mass stars live longer. So the high mass stars have all died, the low mass stars are there. So you find how long a star right there lives, and that determines the age of the star cluster. Because if a star like that lives for 8 billion years, all stars that live less than 8 billion years are dead. All stars that live longer than 8 billion years are still alive, so the star cluster is 8 billion years old. If that turnoff point is a star that lives for like 4 billion years, that means that all stars that live less than 4 billion years are dead. All stars that live more than 4 billion years are still alive. And so that means the star cluster is 4 billion years old. So the turnoff point is how you figure out the age of a star cluster. One little footnote that goes with this is there's occasionally a stray star that never left the main sequence. We call that a blue straggler. Now, a blue straggler, for a long time, they were kind of wondering what caused it. And so the question is, what would cause a blue straggler? So you think about it, you say, well, something must have interfered with it that kept it from leaving the main sequence like it's supposed to. And so what would do that? Well, what would do that turns out to be if it's a binary star. So sometimes binary stars don't behave the same way. The blue stragglers, we'll ignore them for now. So what you do is you look at the turnoff point. We know from before that the particular spectral type or the B minus V color index is related to mass, and that determines the main sequence lifetime of the star cluster, of that particular star. And so you just find the particular type of star that's at the turnoff point, and now you have a measure of the age of a star cluster. So star clusters that have a turnoff point that's very, very hot, early stars, those are young star clusters. Turnoff points that are further down the main sequence are old star clusters.